all light is electromagnetic waves. So some sort of oscillations in what? And that was kind of the question. But the rules of electricity magnetism said there should be these waves, which later shown to be consistent with being light waves. They should travel at this speed. But the two main questions right after we did this were, number one, waves in what medium? Waves through what? You have waves in them. Remember, sound waves. Sound waves are waves in air. Water waves are waves in water. These electromagnetic waves, what are they waves in? What is the medium they're traveling in? And the second, as we just discussed, is here's the speed. Well, speed is relative. This is a speed 3 times 10 300 million meters per second. Pretty fast. What is the speed relative to? What reference frame is that number relative? The answer to these questions in the last part of the 19th century was that there would be something called the luminiferous ether. Heard of the Lewis phrase. The luminiferous ether would be, there must be some sort of medium, which we'll call the ether, through which this light travels. And the speed at which these waves the light rays are traveling depends on where you are relative to this medium. So let's compare water waves. So here, let's say a body of water, like Hudson River. And so there's water there, and then in that water there are some waves. Right? So suppose the river is not moving. Now, you may not know this about the Hudson River, but the Hudson River sometimes doesn't move. Sometimes it flows that way, sometimes it flows that way, sometimes it doesn't move. So we'll take a moment when it stops moving. And imagine you have a boat going by, create some waves, you splash the water up and down, and create some waves. And you see these waves moving across at some speed. So those waves move at some speed in water, the speed of water waves. But now suppose the water, the background water, the body of water, Hudson itself, is moving, and there's a current. So you're sitting there on the bank, and you're watching waves. But now the speed of the waves depends on the speed of the waves relative to the water, and the speed of the water itself, the current. So now the river is moving to the left. The water is moving at the same speed as before relative to the waves moving at the same speed before relative to the water. But you don't see the waves moving as quickly. Because the waves move at a certain speed relative to the water, not relative to you. Or you can do it the other way, suppose it's flowing upstream. Suppose the current is going that way. Have the waves move at the exact same speed relative to the water. And now they look like they're moving faster. So the idea was the same thing must be true for light. There must be some sort of medium through which light moves through. And how fast light goes depends on how you're moving relative to the medium. If that medium is moving by you, then light must go a little bit faster in that direction. If moving by you this way, it must go a little faster in this direction. Now the difference between water or air, right, this is another example of these sound waves, right? If sound moves at about 330 meters per second. So I sound my fingers, that creates a wave that propagates through the air to you. And it takes a certain time to get there. If there's a wind blowing this way, then I snap my fingers, and it takes a little bit longer for that sound to get to you, because the medium itself is also moving. It's got like the waves that fight against that. Right? If the wind is blowing this way, then I snap my fingers, that sound goes faster. So the speed depends on the fluid that we're surrounded by. And the idea is that maybe there's a fluid in which we're all embedded in all the time that carries light. And we must be embedded in that fluid because we can see light from everywhere. And unless light, not only can sound travel from you, but light can travel from you, right? Or you to me, and that's why you can see me. But the strange thing about this material is, unlike air or water, which are confined to the earth, the luminous ether must be everywhere. I can see the sun. Right? The sun is emitting light, and that keeps going through space. That must mean that, in fact, all space has this ether. If it wasn't there, I would get I would see no light. And I know there's no air up there, and so therefore there's no sound up there. There's no water up there, so there's no water waves. But there are light waves, so there must be a light which surrounds all space. So now comes this sort of crucial experiment, which is, okay, so if there's this material there, just like the water in the Hudson River, what reference plane is it at rest relative to? This introduces kind of a special reference frame. There's this medium sigma, there's some sort of fluid or liquid or something that's filling all space. from some perspective, it's still. From some perspective, you're moving through it. In some perspective, it's still. And that sort of tells you that, oh, there's something really special about this. This medium must pervade all space onto the farthest galaxies and stars. It must be out there. And it must be at rest relative to some reference frame. What is that reference frame? Moreover, just the same way as if this is moving in some direction, there's a current to this, that would change the speed of light, depending on which way this fluid is flowing. So the following experiment is devised. Well, look, the Earth moves and rotates. So as it moves and rotates, first of all, it's spinning around, and then it's also orbiting around the sun. So its orientation is changing, its speed and the direction of its speed is changing all the time. What that would mean is if there's a fluid pervading all of space, then the direction of the currents of that fluid that flows by it must change. So suppose we're still, right now, relative to the fluid. Well, in 3 months, we're going to be going, the entire planet is going in an entirely different direction. In 3 months, we're not going this way. We're over here, we're going this way. So if we're still now, if we go a different direction, 3 months later, we'll see different currents. And we'll see a different speed of light. So what you need to do is you need to very carefully measure the speed of light as the Earth changes its orientation, as it changes its position in space, as it changes the direction it's going. And based on the different speeds, you can tell where this ether is and what its reference frame is. Where is it at rest? So the experiment to do this is known as the Michelson-Morley experiment. It was actually first run just by Michelson himself, which was not quite sensitive enough to detect this. But then Morley was adding additional ideas. And the idea behind the experiment is to take a beam of light. So here's a light source back here. And we're going to send it to this mirror here, and this mirror is called a half silver mirror. So the reason why mirrors reflect is they've got silver, aluminum, or some metal on the back and they reflect off light. But instead of putting full backing, we took only half of the backing on it. So we sprinkled just half the aluminum or the silver you want on there. And so half the light goes through and half doesn't. So you get two different beams, one going one direction, one going the other way. And then based on how they travel and come back, you can tell, does light go faster in this direction or does it go faster in this direction? So I send up light that way into one arm of this device, and other light that way into another device. So see, is it faster going that way or that way? And if the ether is flowing this way, then it's faster going that way. And if the ether is flowing that way, it's faster going that way. And if ether is going that way, then they're both going to be the same. But I just turn the whole device, and now I'm like, oh yeah, it's faster going that way, not that way. So to turn this whole device, you actually put the entire thing in a pool of mercury, floated the entire device, and just gently do it. So this is a way of experimenting called an Michelson interferometer. And figuring out, okay, which way is light move fastest? We'll rotate this around different directions. The Earth will rotate as well. It also orbits the sun. So we're going to get all different possible directions, so we can send light this way, and this way, and this way, and this way. We'll move this way, and this way as the planet orbits around. Which way does light move fastest? Which way does light move the slowest? And based on that, where is this medium? Where is its reference frame? Now the surprising result was the speed was the same no matter what the orientation, or the time of year, or time of day, or what direction they sent light. Didn't matter. So that's pretty peculiar, because if you did this with water or sound or anything else, you would detect which direction the wind is blowing. But with light, it didn't work. So that's the second ingredient in Einstein's theory of relativity.